Over 10,000 perfectly good fighter aircraft were completely destroyed before they ever saw a single enemy fighter in the sky, wrecked not by hostile fire, but by the very runways they were attempting to take off from. This staggering peacetime and training attrition rate belonged to the Messerschmitt Bf 109, an aircraft deliberately saddled with a deeply flawed, narrow-track landing gear system that practically guaranteed a violent ground loop if the pilot lost concentration for even a fraction of a second. Chief designer Willy Messerschmitt had engineered the main landing gear legs to mount directly to the fuselage rather than the wings, a brutal compromise that made manufacturing incredibly fast, but created a terrifyingly unstable tricycle on the ground. It was an engineering decision that killed hundreds of green trainees, yet it was the exact same uncompromising design philosophy that birthed the most successful and mass-produced fighter aircraft in the history of aerial warfare. The story of the ME-109 is one of absolute mechanical extremes, where pilot safety and basic comfort were entirely discarded in the ruthless pursuit of raw aerodynamic performance and massive industrial output. In the early 1930s, the newly formed German Aviation Ministry, operating covertly under the lingering shadows of the Treaty of Versailles, secretly issued a requirement for a modern single-seat monoplane fighter. The prevailing military doctrine of the era across Europe was still heavily influenced by the dogfights of the First World War, with many conservative tacticians favoring highly maneuverable biplanes equipped with low wing loading and open cockpits to ensure maximum pilot visibility. However, Willy Messerschmitt, operating out of the Bayerische Flugzeugwerke, fundamentally rejected the idea that a modern fighter needed to be a slow-turning, agile dogfighter. He strongly believed that the future of air combat belonged entirely to the energy fighter, a radically different type of aircraft that utilized superior speed and climb rate to dictate the terms of the engagement, striking violently from above and breaking away before the enemy could possibly respond. This emerging philosophy demanded an airframe that was as small, light, and aerodynamically slick as physically possible, wrapped incredibly tightly around the most powerful piston engine available. At the time, traditional and respected aircraft manufacturers like Heinkel and Arado were building sturdy, somewhat over-engineered machines that were relatively forgiving to fly, but suffered heavily in overall top speed due to aerodynamic drag. Messerschmitt took the completely opposite approach, treating the airframe not as a comfortable vehicle for the pilot, but as little more than a minimalist, lightweight envelope designed to carry a massive engine and a pair of machine guns into the sky. This relentless, obsessive focus on weight reduction led to a series of brilliant structural innovations, including a monocoque fuselage constructed from exceptionally thin duralumin sheets, which entirely eliminated the need for heavy internal bracing and complex struts. But this radical lightweight design came with a profound, unavoidable cost, as the resulting aircraft was notoriously cramped, incredibly demanding to fly at the outer edges of its performance envelope, and notoriously unstable during low-speed maneuvers. The German High Command was initially deeply skeptical of this fragile-looking machine, but when the early prototypes shattered the competition in high-speed dive trials during 1935, the ministry had virtually no choice but to award the massive production contract. If detailed breakdowns of aviation history and engineering interest you, subscribe. I've got more of these coming. The true engineering triumph of the ME-109 was deeply rooted in its highly controversial wing design, which stood as an absolute masterpiece of early aerodynamic problem-solving. Because Messerschmitt had stubbornly insisted on an exceptionally small wing area to aggressively reduce drag and maximize top speed, the aircraft suffered from dangerously high wing loading, which in standard aerodynamic theory results in a lethally fast stalling speed. To solve this critical aerodynamic crisis without increasing the size of the wing, the engineers heavily relied on automatic leading-edge slats, which were sophisticated metal panels that sat flush against the front of the wing during high-speed, level flight. When the airspeed dropped significantly during a dogfight, the shifting air pressure would physically suck these slats outward on mechanical tracks, re-energizing the boundary layer of air flowing over the wing and artificially increasing lift. It was a brilliant mechanical solution that required zero pilot input, but during tight combat turns, the slats would violently snap open and closed asynchronously, causing a sudden, jarring shudder through the airframe that terrified inexperienced pilots into instantly backing off the controls. This delicate balance of aerodynamic compromises naturally extended to the tail section of the aircraft, which featured a highly unique adjustable stabilizer instead of the traditional trim tabs used by the rest of the world. Most contemporary fighters, such as the British Supermarine Spitfire, use small, hinged tabs on the rear elevators to easily relieve control stick pressures for the pilot at different speeds, requiring only a gentle twist of a dial. Messerschmitt engineers vehemently argued that traditional trim tabs created unacceptable aerodynamic drag, so they designed a complex mechanical wheel in the cockpit that physically pivoted the entire horizontal tailplane up or down to trim the aircraft. While this drastically reduced drag and contributed heavily to the phenomenal diving acceleration of the aircraft, it also meant that a pilot caught in a sudden high-speed dive had to desperately crank a heavy mechanical wheel to avoid flying straight into the ground. Countless pilots found themselves physically unable to pull out of extreme high-speed dives because the control surfaces would effectively lock up under the immense airflow, forcing them to use both hands to haul back on the control stick while frantically adjusting the tailplane angle. To physically propel this tiny, dangerous airframe through the sky, the German aviation industry provided what was undeniably the most advanced piston engine of the late 1930s, the Daimler-Benz inverted V12 engine. By turning the traditional Va-12 engine entirely upside down, with the heavy cylinder heads pointing toward the ground and the crankshaft sitting at the absolute top, the engineers achieved several massive tactical advantages simultaneously. The inverted design drastically lowered the aircraft's center of gravity and allowed the massive propeller shaft to be positioned much higher, which provided necessary ground clearance for the propeller blades, while keeping the nose profile incredibly sharp and sleek. More importantly, it provided the pilot with a beautifully unobstructed view directly over the nose, a crucial visibility advantage in a deflection shooting engagement that traditional upright engines utterly blocked. However, this inverted orientation meant that the vital spark plugs and exhaust manifolds were buried deep at the absolute bottom of the engine compartment, where they were highly susceptible to constant oil fouling and presented an absolute nightmare for freezing ground crews attempting routine maintenance. The undisputed masterstroke of the massive Daimler-Benz engine, however, was its highly advanced fuel delivery system, which completely abandoned traditional float carburetors in favor of direct mechanical fuel injection. In the early years of the Second World War, British fighters entirely relied on standard float-type carburetors, which functioned perfectly under normal positive gravity conditions, but failed catastrophically the moment a pilot pushed the nose down into a sudden negative G dive. The liquid fuel inside the British carburetors would literally float to the top of the chamber, instantly starving the engine of fuel and causing the opposing fighters to abruptly sputter, backfire, and lose power during crucial evasive maneuvers. The ME-109, equipped with complex high-pressure mechanical fuel injection pumps, could violently snap into a steep dive at any given moment, allowing German pilots to simply push the stick forward and instantly vanish from the gun sights of their pursuing British counterparts. This single technological advantage entirely dictated the tactical geometry of air combat over Europe for over 2 years, forcing Allied pilots to develop complicated, significantly slower half-roll maneuvers just to follow a diving Messerschmitt. But the unbridled power of the direct-injected V12 engine naturally generated an immense amount of waste heat, which required a complex liquid cooling system that proved to be one of the aircraft's most fatal vulnerabilities. Messerschmitt utilized a pressurized mixture of water and ethylene glycol, which allowed the liquid coolant to operate at temperatures well above the normal boiling point of water, thereby requiring much smaller, more aerodynamically efficient radiators. These low-profile radiators were cleverly tucked underneath the wings, utilizing a specialized boundary layer bypass flap system to significantly reduce the immense drag typically associated with heavily liquid-cooled aircraft. While brilliant on a drafting table, this widespread placement meant that a single stray bullet from an enemy machine gun could instantly rupture the delicate radiator system, venting the superheated coolant into the atmosphere and causing the massive engine to seize in under 3 minutes. Translating all of this engine power into actual thrust presented yet another complex engineering hurdle, which the Germans initially solved using the Vereinigte Deutsche Metallwerke electrically operated constant-speed propeller system. Early models of the Bf 109 required the pilot to manually adjust the pitch of the propeller blades using a toggle switch mounted directly on the throttle quadrant, constantly changing the blade angle to maintain optimal engine revolutions per minute. Much like shifting gears in a manual transmission sports car, the pilot had to shallow the blade pitch for takeoff and climbing, and then bite deeper into the air for high-speed cruising or diving. During a frantic dogfight, this manual electric system created an absolutely massive workload, as the pilot had to simultaneously fly the aircraft, manage the throttle, clear their tail, and rhythmically flick the propeller pitch switch to keep the engine from catastrophically over-revving. It was not until the later Friedrich and Gustav variants that fully automatic mechanical governors were finally introduced, mercifully taking this heavy cognitive burden away from the exhausted pilots and allowing them to focus entirely on aerial gunnery. The inverted engine design also directly paved the way for another lethal innovation that would permanently define German fighter design: the engine-mounted cannon, known universally in German aviation terminology as the motor Kanone. Because the inverted V-12 placed the wide cylinder banks extremely low and the narrow crankshaft high, the engineers realized they could mount a heavy 20mm autocannon directly behind the engine block itself. This incredibly clever arrangement allowed the explosive shells to fire straight through the hollow center of the spinning propeller hub, completely eliminating the severe convergence issues that constantly plagued fighters heavily reliant on wing-mounted machine guns. A pilot flying the Messerschmitt did not have to worry about complex deflection calculations regarding wing gun convergence distances. Wherever the sharp nose of the aircraft was pointed, the explosive cannon shells traveled in a perfectly straight, devastatingly accurate line. However, the violent recoil and harsh mechanical vibrations of firing a heavy cannon bolted directly to the engine block frequently shattered the delicate engine mounts, cracked hydraulic lines, and routinely vibrated the analog instrument panels entirely off their mounts. Stepping into the actual cockpit of a mid-war ME 109 was an exercise in extreme claustrophobia, a startling physical reality that veteran pilots noted with a bizarre mixture of deep affection and sheer terror. The canopy was essentially a highly narrow, angular greenhouse constructed of heavy, flat armored glass panels held tightly together by a thick steel framework, leaving the pilot with practically zero rearward visibility and barely enough physical room to turn their head. Once firmly strapped into the unpadded bucket seat, the pilot's shoulders physically touched the metallic sides of the fuselage, and the heavy control stick was positioned so uncomfortably close to the chest that applying full aileron deflection often required awkward physical contortions. During fierce combat operations, this severe lack of visibility meant that German pilots were essentially fighting blind in their crucial rear hemisphere, forced to constantly weave and violently kick the rudder pedals just to see if a hostile fighter was sneaking up behind their massive tail section. It was a hostile, unforgiving environment that ruthlessly punished physical fatigue, where a pilot flying their third stressful combat sortie of the day had to wrestle with increasingly heavy mechanical controls in a sweltering aluminum tube. Knowing what you now know about its historical performance and severe engineering compromises, do you think this uncompromising design approach was the right call for its era? Share your thoughts below. When the ME 109 was first unleashed upon the world during the Spanish Civil War, and subsequently during the lightning-fast invasions of Poland and France, it operated in an environment completely and perfectly suited to its inherent strengths. It dominated the European skies as a purely tactical air superiority fighter, easily outpacing and severely outclimbing the obsolete biplanes and early monoplanes fielded by its desperate adversaries. German pilots racked up staggering kill counts using highly disciplined hit and run energy tactics, utilizing the immense climb rate of the Messerschmitt to simply dictate when and where a fight would take place. But the strategic landscape shifted drastically and permanently during the long summer of 1940, when the German Air Force was explicitly tasked with establishing absolute air superiority over the English Channel during the Battle of Britain. Suddenly, the lightweight, highly specialized, short-range design philosophy of Willy Messerschmitt became a massive, glaring strategic liability, as the tiny fighter possessed an internal fuel capacity that allowed for barely 80 minutes of total flight time. By the time a German pilot formed up into a massive armada over occupied France, slowly crossed the wide channel, and successfully engaged the Royal Air Force over the skies of London, they practically had the analog low-fuel warning light flashing directly in their eyes. This left them with a truly meager 10 to 15 minutes of actual aggressive combat time before they had to abruptly break off the engagement, drop their nose, and carefully glide home over the freezing, unforgiving waters of the Channel. This terrifying range limitation deeply and permanently impacted the psychology of the German fighter pilots, who spent almost as much time anxiously staring at their analog fuel gauges as they did frantically scanning the horizon for British Spitfires. The highly advanced British coastal radar network allowed the Royal Air Force to patiently loiter over their own airfields, effectively ambushing the German formations, exactly when they were at the absolute limits of their operational endurance. While German engineers desperately scrambled to design and manufacture external drop tanks to artificially extend the aircraft's range, crippling bureaucratic delays meant these absolutely vital modifications arrived far too late to alter the outcome of the campaign. Forced to fly as highly vulnerable, close escort for slow, heavily laden bombers, the Messerschmitt pilots were entirely stripped of their primary tactical advantage of high-speed energy tactics, forced to slowly react to British attacks rather than initiate them. The operational narrative of the aircraft changed completely once again when the German military initiated the massive invasion of the Soviet Union in 1941, opening a brutal theater of war where the Me-109 found its ideal combat environment. The immense air war on the Eastern Front was primarily a low-altitude tactical struggle, fought aggressively in the dense, freezing air below 15,000 feet, where the supercharged Daimler-Benz engine performed with terrifying lethality. At these lower, thicker altitudes, the F variant of the Messerschmitt, commonly known among pilots as the Friedrich, possessed a massive power-to-weight advantage over the crudely built and poorly equipped early Soviet fighters. Unburdened by the strict requirement to fly high-altitude strategic escort missions for heavy bombers, German pilots gleefully reverted to their highly preferred energy-fighting tactics, diving out of the brutal winter sun to shatter Soviet formations in a single devastating pass. This specific environment allowed legendary fighter aces like Erich Hartmann to compile completely unprecedented and frankly staggering combat records, with Hartmann alone claiming 352 confirmed aerial victories entirely from the cramped cockpit of a Messerschmitt. However, the highly publicized success of the German aces on the Eastern Front often completely masks the incredibly harsh logistical reality of operating such a delicate machine from austere, muddy dirt strips deep within Soviet territory. The notoriously narrow landing gear became an absolute mechanical nightmare in the deep mud and heavy snow of the Russian steppes, sinking deeply upon touchdown and violently flipping hundreds of precious aircraft onto their backs. The heavily specialized ground crews had to construct immense wooden tripods out of local timber and use heavy iron chain hoists just to lift the massive engines out of the airframes in sub-zero blizzards, fighting a continuous war of attrition against the elements. To make matters significantly worse, the advanced metallurgy used in the construction of the massive Daimler-Benz engines introduced an entirely new, deeply terrifying hazard to the pilots flying them over the vast Russian landscapes. In their obsession with weight reduction, German engineers had utilized electron, a highly advanced magnesium alloy, to cast the large engine blocks and supercharger casings. While this incredibly light metal saved dozens of crucial pounds, magnesium is highly flammable when exposed to extreme heat, meaning that a single incendiary bullet from a Soviet machine gun could literally ignite the entire engine block itself. Once an electron engine block caught fire, it burned with a blinding, intense white heat that could not be extinguished by normal means, rapidly melting straight through the duralumin engine cowlings and completely consuming the aircraft in seconds. As the terrible conflict dragged endlessly into its final, desperate years, the severely aging Me-109 was forced into yet another operational role it was absolutely never meant to perform: high-altitude point defense against massive formations of American heavy bombers. The United States Army Air Forces began fielding massive daytime armadas of B-17 Flying Fortresses and B-24 Liberators, eventually protected by heavily armed P-51 Mustangs that could comfortably fly all the way to Berlin and back. To physically counter this existential threat, German engineers desperately upgraded the aging Messerschmitt airframe, installing massively uprated engines equipped with complex water methanol injection systems. This specialized chemical injection forcefully cooled the intake charge, allowing the supercharger to push sudden, violent bursts of raw horsepower into the engine to quickly claw up to bomber altitudes. To physically fit these massive new superchargers, heavy cowl-mounted machine guns, and enlarged engine blocks into the tiny 1930s airframe, engineers were absolutely forced to bolt ugly, bulging aerodynamic blisters onto the nose and wings of the aircraft, These infamous, highly drag-inducing bumps, universally and derisively referred to by German pilots as Boule, significantly increased aerodynamic drag and made the once nimble aircraft highly sluggish and deeply unresponsive at high altitudes. The final heavy production variants of the war, such as the Gustav and the late war Kurfürst, were absolute mechanical monsters compared to the lightweight scalpels that had flown so gracefully during the Battle of Britain. They were incredibly heavy, brutally powerful, and heavily armored, fully capable of unleashing a devastating torrent of heavy 30mm cannon fire, but they were almost hopelessly outclassed in a high-speed dogfight against the sleek P-51 Mustang. Furthermore, the highly structured German pilot training program had entirely collapsed by late 1944 due to extreme fuel shortages, meaning that these unforgiving, wildly overpowered, and nose-heavy machines were being desperately handed to terrified teenage recruits. These young men often entered combat with barely 50 hours of total flight time, completely lacking the highly developed muscle memory required to keep the heavy fighter from killing them during a simple takeoff roll. The terrifying combination of a highly unstable aerodynamic airframe, a massive engine torque that violently pulled the aircraft to the left on takeoff, and completely inexperienced pilots resulted in a terrifying spike in non-combat fatalities. The vicious ground-looping characteristics of the narrow landing gear ultimately claimed the lives of thousands of desperate young pilots as they struggled simply to get off the cratered runways of the rapidly collapsing Third Reich. When placed directly beside its most famous contemporaries, the ME-109 presents a truly fascinating study in wildly competing national aviation design philosophies. The British Supermarine Spitfire was an absolute triumph of aerodynamic elegance, utilizing a massive elliptical wing to generate incredible lift and turn performance, creating a forgiving aircraft that a skilled pilot could practically dance through the sky. The American P-51 Mustang was a complete masterpiece of mass production efficiency and highly advanced laminar flow aerodynamics, possessing massive internal fuel tanks that effortlessly allowed it to project tactical power across entire continents. In stark, brutal contrast, the Messerschmitt was a pure, brutalist exercise in mechanical packaging, an aircraft that entirely ignored basic pilot comfort, operational range, and landing safety in order to extract the absolute maximum possible kinetic performance from the smallest possible physical package. Even when compared to the FW-190, Germany's wildly successful other legendary fighter aircraft, the Messerschmitt was vastly inferior in ruggedness and pilot ergonomics, yet it remained the backbone of the fighter force because its highly modular design allowed desperate factories to continuously churn them out by the tens of thousands. The historical enduring legacy of the ME-109 is uniquely complex, forever tied directly to a political regime of completely unprecedented cruelty, but simultaneously standing tall as a brilliant monument to sheer engineering audacity. It is a deeply compromised aircraft that was undeniably obsolete by the final bloody years of the war, stretched incredibly far beyond the absolute structural limits of its original 1930s design parameters. Yet, it remained a highly lethal, terrifying threat to Allied aircrews until the very last day of the global conflict. More than 33,984 examples were successfully built, officially making it the most heavily produced fighter aircraft in all of aviation history, a staggering industrial record that will almost certainly never be broken by modern aerospace manufacturing. It successfully taught the entire world that raw vertical energy and absolute speed could utterly defeat traditional horizontal maneuverability, a foundational tactical lesson that completely rewrote the complex rulebook of aerial warfare. The brutal, unvarnished truth of the ME-109 is that it was simply not a good airplane in the traditional comfortable sense. It was physically exhausting, extremely dangerous to its own highly trained pilots, and practically blind to the rear hemisphere. But as a pure, completely uncompromising weapon of war, deliberately designed to perfectly translate sheer horsepower into deadly, inescapable tactical energy, it was a terrifyingly brilliant piece of engineering that shaped the world. Long after the massive German factories lay in smoldering ruins and the geopolitical maps of Europe were completely redrawn, the profound influence of Willy Messerschmitt's lightweight, massive engine philosophy heavily continued to echo through the design bureaus of the early Cold War. The basic concept of wrapping the absolute smallest possible aerodynamic envelope directly around the largest possible power plant became the exact, highly effective blueprint used to create the supersonic jet interceptors of the very next generation. If you found this historical analysis useful, a like helps more people discover these deep dives. Thanks for watching.